Okay, let's look at how we can combine some capacitors in parallel and series and look at some energy and stuff like that. Okay, so let's say we're doing lab experiments and we're building capacitors out of tinfoil like we did, and we were having a contest. We want to make the most capacitance. Say four of the groups decided to work together. So three groups made regular capacitors, like a little bit bigger, 0.04 by 0.25, so 40 centimeters by 25 centimeters, pieces of tinfoil, and they put some paper, it has 3.1 for its dielectric constant, and the separation was 0.1 millimeters. All right, but group 4 decided to get creative and make a spherical capacitor. Instead of making parallel plates, they're going to make a spherical capacitor, which is like a ball of tinfoil with the wire stuck into it. So we're going to have to, because we have to bring electrical connection out. So a ball of tinfoil of radius A, 2 centimeters. And then their dielectric, they decided to paint, because we looked up and paint has a dielectric constant of 7. So somehow they magically painted a 1 millimeter coating and got it dry in time, and no gap so that the tinfoil doesn't touch each other. And then they covered it with a new layer of tinfoil that is covering the whole outer sphere. Okay, so first off, let's find what the capacitor values are for each of these teams, and then we'll think about how can we put them together to get the most capacitance out. All right, so C1, 2, 3, we'll just call it C1. They're all the same. We're going to use the regular formula for parallel plates, kappa epsilon naught A over D, right? And so kappa for the paper, we said it was paper, is just 3.1, epsilon naught 8.854, 10 to the negative 12. A, we said we had 25 centimeters by 40 centimeters. So converted to meters, we got that. This is multiplying, and then we'll divide by D, which is 1 times 10 to the negative 4 meters. All right, so our capacitance value, 3.1 times 8.854 E negative 12 times 0.225 times 0.44 divided by 1 E negative 4. 27 nanofarads. All right, so that's what the first three teams got, something like that, we'll say. And then we've got team 4 made a spherical. All right, this is an equation. I don't know if it's on your equation sheet. You might want to add it to your equation sheet. 4 pi epsilon naught, I think is all, if I recall, is all on the top. 1 over A minus 1 over A minus 1 over B, where B is the radius of the outer shell, and so it would be just the 2 centimeters plus the 1 millimeter, right? And so A is radius of the inner, B is radius of the outer, and it's the difference that goes down here. And so, oh no, there needs to be a kappa here somewhere too. Okay, I believe that's the right equation. Let me just take a peek here. I think I have it written on the back here. 4 pi, yes. Okay. So putting in numbers, 4 pi epsilon naught 8.854 10 to the negative 12. We said this kappa was 7. And then we have A was 2 centimeters, so 1 over 0.02 minus B, which is the second tinfoil, 1 over 0.02 plus 1 millimeter, 0.001. This is all meters. Alrighty, let's plug that in. 4 pi epsilon naught. I think it would take that as times, but let's just put a times in there just in case. 4 pi epsilon naught times 7 divided by, and we need some parentheses here, 1 divided by 0.02 minus 1 divided by 0.021. Yes. Okay, looks like it interpreted things right. So this one is just 327 picofarads. So 0.327 nanofarads. All right, so that one didn't do too well by itself, but we'll go with it. So how should they connect these up? So we're going to use these together to make one bigger capacitance. Remember our equations for combining capacitance. C series is 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C4, since we have 4. All right, so what would that be? 1 over, these are all the same, so we have 3 times 1 over 27.4 nanos. It's going to just, everything is going to be nanos, so we'll end up with an answer in nanos. So let's leave this as 27.4 plus 1 over 0.327 nanos. All right, so if all the C's are in nanos, then you're going to have 1 over nanofarads, so the answer is going to come out in nanofarads if you just leave these like this. So just be careful with your units, but you can do that. And so we get 1 divided by 3 times, in parentheses, 1 divided by 27.4. And then that is plus 1 divided by 0.327. Alrighty. 1.03 nanofarads. So that is not correct. Look how it interpreted it. And how do I know it's incorrect? Because when we combine things in parallel, the combination will be less than any of the things. So let's fix this. 1 divided by, opening parentheses, 3 times 1 divided by 27.4. Let's put that in parentheses, and let's get some more parentheses. If you want all this to be on the bottom, we want it to not do that weird thing, making it partially on the top, partially on the bottom. So that gets added to, still on the bottom, 1 divided by 0.327. That looks better. And so we get 0.316. 0.316 nanofarads. So definitely not the way to go, combining things in parallel. Just a little side note, what if we just had the 3 that were equal, right? What would happen if those were the only 3 in parallel? So when we divide by a fraction, we flip over and multiply, so it ends up being 27.4 divided by 3, right? And that's kind of the general rule. If you have 2 capacitors, say they're both 1 microfarad, you combine them in parallel, you get half, right? And so if you have 3, you get a third. If you have 4, you get a fourth. You can kind of see that. You can do this as call these C's. I guess we can do that in a minute. So C series, 1 over C plus 1 over C. If we just did 2, right? 2 that were equal. So you get 1 over 2 over C. When you divide by a fraction, you flip and multiply. So that's equal to 1 times C over 2, which is C over 2. Right, and so that's the same thing. No matter how many add, the number of capacitors will be in the bottom. So we're just going to keep getting smaller and smaller capacitances if we combine in parallel. So that's not the way to go. I'm sorry, in series. So let's combine in parallel. Parallel just means we add them up. So C1 plus C2 plus C3, C4, which is 3 times C1 plus C4, 3 times 27.4. plus 0.327, 82.5. This is all nanofarads. So this is a new C total. parallel. All right, so definitely when you're combining capacitors, if you're going for bigger, you combine them in parallel. Okay, so try parallel and series to see how they should connect. Parallel is the way to go. Okay, what is the most C? We already did that. 82.5 farad, 82.5 nanofarads, and the most potential energy if charging at 10 volts. Okay, so we want to calculate PE max also. We have several different equations for potential energy of a capacitor, stored in a capacitor. Where are they? Here we go. So we have 1/2 CV squared, 1/2 QV, 1/2 Q squared over C. All right, so for this capacitor, we got its capacitance, and it just said we're using 10 volts. So we know C and V. Where did we go here? So let's use this version since it has C and it has V. We could calculate the charge because we know that somewhere it says Q equals VC. Yep, so we can relate them. They're all just the same equation with different versions of QVC substituted in. But let's go with 1/2 CV squared. So 1/2 CV squared. And so 1/2 of 82.5 times 10 to the negative 9 farads times 12 volts squared. Not 12 volts, I said 10 volts. 10 volts squared. So we got 100, well, let's just put it in there, 0.5 times 82.5 e negative 9 times 100. So the maximum potential energy is just 4.13 times 10 to the negative 6, so microjoules. Okay, so is that all we want to do for this? Yeah, let's go ahead and stop there.